start talking about proofs and the types of proofs that you'll see in this class. First, the main proof that you're going to work with is called a two-column proof. Can make a T-chart. Statements go on the left. Those are the things that you can say. Reasons go on the right, and that's just why you can say it. Typically, a reason will be either a property, a theorem, a definition, or an explanation. Definition. But everything you say in a proof has to be backed up. It has to hold up to a why. And you do that by stating a property, a theorem, a definition, or an explanation. Another pretty common type of proof that we're going to work with is called a flow proof. And they use boxes that will have a statement and a reason, and then connect to another box that has another statement and another reason with an arrow. Sometimes there might be two boxes that lead into one, or even three boxes that lead into one. But the statement goes on top of the box and the reason on the bottom of the box. The third type of proof that we might see is a paragraph proof. Usually it's a good idea to start with a two-column proof, kind of like an outline, but then you have to turn it into a paragraph. Complete sentences, correct grammar, punctuation, spelling. So when we talked about a two-column proof, we said you can back up all of your statements with reasons, and those reasons can be properties, theorems, postulates. So here's a bunch of properties that you actually learned in algebra. There's the addition property of equality, or subtraction, multiplication, and division. All four of them are basically the same thing. You maybe don't remember them by name, but you remember how to use them. It's what you do to both sides of the equation when you're solving it out. If you're solving for x and you had to subtract on both sides of the equals, that's the subtraction property of equality. If you were solving for x and you had to divide by both sides, or divide something on both sides, that's the division property of equality. It's what you do on both sides of the equals when you're solving. We've also got the substitution property. When you know what something is equal, you can substitute it into an equation. So here we know that B equals D. So that means that instead of B, you can replace it with D, substitution. Then there's the transitive property, which is a lot like substitution. If A equals B and B equals C, they both have B in it. It's kind of like the middleman. B is the middleman. You can eliminate the middleman and just go straight A to C. The difference between substitution and transitive is transitive can only be equals. Substitution can have like plus and minus and stuff in it. Transitive is if they only have equals. Substitution is if there's a plus or a minus in it. Then there's the reflexive property. Like looking at a reflection, you see the exact same thing on both sides of the equals. It's the exact same thing on both sides of the equals. And the symmetric property. We learned about symmetry in the last unit. If there's a line of symmetry, that means you could like flip it over that line of symmetry. And that's exactly what's happening here. You're flipping over the line of symmetry. A equals B, B equals A. You just have to flip the order because it's flipped over the line of symmetry. So those were a bunch of the properties that you could use. This comes from stuff that you might be told or you might see in a picture to start a proof. So here we have congruent segments, two segments that are congruent. We know they're congruent because they have these little tick marks. Those tick marks show that those two segments are congruent. And then since they are congruent, we can write that they are congruent. Segment AB is congruent to segment CD. Here, we're told that if this is a bisector, bisect means cut in half. So if this is a bisector, that means MN is cut in half, which means you got two equal sides or two congruent sides. If it bisects, it cuts it into two equal pieces. So that means that MA is congruent to AN. Now, going from knowing something's a segment bisector to that statement, that MA is congruent to AN, you're going to have to back that up with a reason, because this is our statement. Your reason is to be a definition, a property, or a postulate or theorem. This would be a definition. Definition of bisect. Bisect means cut into two equal pieces. There's our two equal pieces, two congruent pieces. So this is already kind of in a box. That would be, if that is just in a box and that were to flow into another one, that's a flow proof. Right there, we've got a statement and a reason in the box. If this was two column, then this would be on the left side, and then definition of bisect would be your reason on the right side. So very similar to what we just had. If B is the midpoint, that means that these two sides are congruent. AB is congruent to BC. Because that's the midpoint. That's the definition of midpoint. And if we're just told that something is in between, picked out these letters to kind of help you remember that this is a duh statement. If U is in between, then we know that du, this first part, plus UH, the rest of it, is equal to the whole thing, DH. Remember, I told you that duh statements are like postulates. This is called the segment addition postulate. So we're going to go through a lot of the same things, but this time with the angles. We got congruent angles. So that means you can say that they are congruent. Angle J is congruent to angle K. And that would either be, that would probably just be given if it's something that simple. Angle bisector. Bisect, again, means to cut into two equal pieces, two congruent pieces. So if it's an angle bisector, you get two congruent pieces. There's one congruent piece and the other congruent piece. So you can write that out. Angle, remember when you name it, the vertex goes in the middle. So F-O-U. Congruent to U-O-R. And again, that's a lot like what we did with the line segments earlier. Definition of bisect. If you've got a point that's inside or a ray that's inside two angles, just like when segments, we know that these two angles will add up to equal the whole angle. So that means the measure of angle TEA plus the measure of angle AEM will equal the measure of the whole thing. The two parts add up to equal the whole. TEM. The two parts add up to equal the whole. That was postulate. This time it was for angles. And a linear pair is two angles that together make a straight line. It says linear, makes a straight line. So that means that angle 3, the measure of angle 3, plus the measure of angle 4 equals 180 degrees, because it's a straight line. That's the definition. So now we're going to work through our very first proof. Now, the best thing about proofs is that you always know where to start. You always start with the given. Every single time. So it's never, where do I start? Where do I start? You always write down the thing that they tell you first. RT is equal to 5x minus 12. And the reason they even gave that to you is given. Then you're going to look at the picture and see if there's anything else that you know besides what was written out for you. So looking at this picture, you can also see RS is equal to 3x minus 8 from the picture. If you said given, that's okay too. It's from the picture. And then similarly, we've got right there, ST is equal to x plus 2. Same thing from the picture. So we have the two pieces, the part that I did in blue, the part I did in green, and then the whole thing. RT is the whole thing. It should remind you and make you think of the segment addition postulate, where we said the two parts add up to equal the whole thing. So let's write that out. The two parts, RS plus ST, add up to equal the whole thing, RT. That's segment addition postulate. So we just made an equation that used RS, ST, and RT. And right before we did that, we wrote down what each of those three things were. RS was 3x minus 8. Plus ST is x plus 2. Equals RT 5x minus 12. So what we just did is we took out the letters and replaced it with the expression. It's called substitution. So now we've got an algebra 1 equation we can solve out. And you really just going to have to ask yourself, how do you solve it? So the first thing that you would do to solve this, or the first thing I would do at least, we got 3x and x on the same side. So I'm going to combine those. 3x plus x, that's 4x. Then we got negative 8 and a positive 2. Negative 6. And what did I just do there? That is called combining like terms. So now we're going to try to finish solving this, hopefully in another step or two. The next thing that we can do to solve would be, we want to get our x's together on one side. So let's move this 4x over. Subtract 4x. Five x minus 4x is just x. And then your reason is always just, what did you just do? So what did we do? We subtracted 4x. So that is the subtraction. Property of equality. Property. Pen started writing weird. And we've got one more step to finish it off. Trying to get x by itself, we would add 12. So you get 6 equals x. We got that by adding to both sides, so that's the addition. Really, that's done. I'm going to add in one more thing just to show you, because sometimes you want x to be on the left side. A lot of times that's the way you prefer to see it, is x equals 6. And we named what that property was earlier, so x equals 6 from 6 equals x. Remember, that's just flipping it over. It's called the symmetric property. The idea with proofs is that you do every single step to get to the conclusion, and you have a reason to back it up. You're backing up everything you say. So that way, if somebody, remember, this is kind of like what lawyers do. If you're to be cross-examined, basically, if they're going to cross-examine your witness, they're trying to find holes in your story. You've backed everything up. They can't break your logic. That's what proofs are all about. Solid logic that can't be broken.